Well, I want to accomplish a couple goals in this particular video. One is to describe torque in maybe a way that you haven't heard it before. And I also want to show you how to perform a math operation known as a cross product. If this is a typical sequence in physics, you've already done one kind of vector multiplication, and that's called a dot product. When you first studied work is the dot product of force and displacement. But when I introduce that, I always say there is a second way to multiply vectors together, and that is called a cross product. So torque is usually the first time you encounter a cross product. So I'm going to describe how to perform a cross product operation in two different ways. I'll start with probably the easier of the two, and then I'll show you the other one. So first, let's just remember what torque is. Torque is the twisting kind of force that causes things to change their rotation. So the way you torque something is you exert a force at some distance away from the rotation axis and at an angle that is not right along the line towards or away from the rotation axis. So in this case here, maybe we've got this swinging bar that's hanging down, and we have the ability to exert a force at this location. So we could not exert a force directly up towards the axis nor directly away, because all that would be trying to push it in or out of the axis. If we want to twist it around, we have to exert a force at some angle. So I'll draw my force vector here in green. Maybe that's a force of 5 newtons, and it looks to be just a little bit below horizontal, maybe 340 degrees. So I'm going to use horizontal here as being 0 or 360. We're maybe 20 degrees below that, so I'll say 340 degrees. So now we have to describe what we call the R vector. I just call it the R vector, and that's the vector that goes from the axis of rotation directly to where that force gets applied. And let's just imagine this is 12 meters, and that's certainly also down in the fourth quadrant, so we're going to say that's at 310 degrees. So you notice I put my vector symbol over my R. I should do the same thing here on my force. So we are going to be multiplying those together. So torque is described as R crossed with F. Now in the case of a cross product, the order is important. So you cannot do F crossed with R, and I'll show you why when we talk about the direction in just a minute. So the first step is to get the magnitude. How big is the torque number? And then we'll talk about how to get the direction. The magnitude part, which we usually write just inside little brackets, that means how big is it? It's the magnitude of each of your two vectors. I guess technically I should have vector symbols over these. It's the magnitude of those vectors times the sine of the angle that the tails of those two vectors make with each other. So you have to imagine sliding, like slide this R vector down so that they're tail to tail, and then you have a little angle in between them. But because of the way I described them, one point's at 310 and the other point's at 340, it's pretty easy to tell that there's 30 degrees in between them. So the magnitude of this would just be 12 meters times 5 newtons times the sine of 30 degrees, which comes out to 30 newton meters. The unit for torque is called a newton meter. You might think, oh, I've seen that before, and we've called that a joule for energy, but we don't call it joules when it's torque. We call it newton meters. So that's the magnitude. I'm writing the Greek letter tau here, kind of sloppy on that one. But now I want to get the direction. So I'm going to show you the right-hand rule for figuring out cross-product directions. And it works like this. You take your right hand, and you imagine curling your fingers in a direction so that the R vector swings towards the F vector. So the R vector, again, is down here pointed at 310. If I want to swing it around so that it points towards the 340, that means I have to go a little bit counterclockwise. So I'm going to spin my right-handed fingers counterclockwise, and then if you look at my thumb, it's pointed right up out towards you. That is the out of the page direction, or in our typical orientation, if we call this way positive X, rightward, and this way positive Y, then out of the page is referred to as positive Z. So we can either write out of the page Or we could just write k hat, because that's shorthand notation for in the positive z direction. So I got my magnitude by doing this operation, that's just a number, and then I had to do the right hand trick to get the direction for the actual torque vector. It's a little weird because there is nothing actually coming out of the page at us, you notice. This is just the direction that we describe for this torque. A better name for this torque vector for most people would be counterclockwise, because that is what the direction that we end up spinning this thing. But in the formal vector notation, counterclockwise always means out of the page towards you. And if we had had a vector, let's say the force vector had been slightly below, so then we would have had to turn the r vector clockwise, then we get a clockwise torque, which is into the page, or negative k hat in the formal vector notation. So that's probably the quick and easier way to do this cross product. Let me show you another way, and that's if you have vector components like the I, J, K notation. So what I'm going to do is I'm going to describe these two vectors in terms of their components. And I figured these out earlier. So again, I'm going to do the problem again. I'll get the same answer. I just want to show you how I get the different answer. So the R vector can be described as 7.7 meters in the positive x direction minus 9.2 meters, that's j hat, or in the y direction. So that's downward and rightward, as you can see here. And then my force vector also has a rightward and a downward component. This was 4.7 newtons I hat minus 1.7 newtons j hat. So there they are in vector form. And get a little more space here I can use. So now I'm going to perform the operation. And when we do a cross product with unit vectors, here's what we do, and it gets a little hairy. I'm not going to show you where this comes from. There's actually a separate video that I'll make on how you do this operation, but we are looking for a vector. So I'm going to write this in component form. My answer will be in component form. So I'm going to have something in the I hat direction or x direction. I'll have something in the y direction, and then I'll have a term in the k hat direction. So what fills in to get these component magnitudes is made up of the components of each of the two vectors. So here's the first one. I got to concentrate while I write this. You use the y component of the r vector, that would be like this, along with a z component of the force vector. Of course, my problem doesn't have 3 dimensions, so I don't have a z direction. That's going to make this nice because that'll be 0. And then you subtract the z component of r times the y component of f. Well, that whole thing is going to be 0 because of the fact that I don't have the third vector component in these. For my j hat component, I need the z component of r times the x component of f, and then minus, and you just flip-flop these. This is the x component of r times the z component of f. And for the final component, also notice that these have z components in them, which again will be 0 for our problem. So now we're going to take rx and fy and minus ry fx. That, of course, we do have. There's those 4 components there. None of those are 0. So only because my problem is simpler can I get this a little faster. So my torque will be, so I'm just going to use this last term here. Again, I got a 0 I hat, 0 j hat. Now I'm going to fill in my components. I have 7.7. I'm going to leave the units out just for a little shorter notation. And then my y component, this is a negative 1.7. And then I'm going to subtract the y component of r, which is a negative 9.2, times the x component of f, which is 4.7. Now watch out for your signs. You have a negative here minus a negative there. And it turns out, I did this math earlier, it indeed gives us 30. I'll put my units back in, Newton meters. And of course, the k hat, because that was the component that I was working on. And that's exactly what we had up here when we did it in the other form. So they do match. So that's a lot there. And again, if you want to see where this came from, you can. It's not hard to find a reference. I think my textbook describes that, and lots of online resources use this. But I will create another short video so you can look for it soon that describes how we get those components there. So if you have a formal torque problem that you have to do involving unit vectors like that, this may be the way you're going to have to approach it. So hopefully that helped you get through those if you need to. Thanks for watching.